Today is January 30th, 2020. It is 10:17 p.m. I'm going to explain to you this patent, disclosure, and application. I am the primary designer of this engine that you're looking at. In a moment, I'll explain the participation of the co-designer of this engine and the advancements of this engine. But first, I'm going to explain the primary design. This is a nominal displacement engine. Okay? It's a nominal displacement adsorption engine. 3-phase, 3-stroke, 1 cycle. You're looking at 3 phases of 1 stroke. This is the compression stroke. This is the expansion stroke. This is the power stroke. Spun counterclockwise. This would technically be down here on the other side of the crank pin in a 1-stroke engine. The outlet fuel is the exhaust coming through this resonant check valve. This is an adjustment for the resonant check valve. There can be 2 resonant check valves with a bypass valve. The exhaust comes into the bottom of the catalyst. The new fuel comes out of the catalyst into the power stroke. As the power stroke expands, it draws in the fuel naturally. As the expansion happens, the adsorption principles take effect and the fuel expands and becomes cold. There's no heat. All of the thermodynamics of the fuel are used up completely in the combustion process. Then they're regenerated and pushed back out to come back into the catalyst. The start time of the patent disclosure and the design that you see here that will be included in the patent paper started at 8:30 p.m. today and finished at 9:30 p.m. today. I gave 1 hour for explanation and discussion. We did it in 48 minutes, 26 seconds, 0.78. I understand this concept. Witness, Anna G. Devine. 1:30:20 at 10:06 p.m. Double quote. Art Devine, Arthur Devine. 1:30:20 at 10:05 p.m. Primary designer, David Puckta, David Allen Puckta. 10:07 p.m. The array can be put in a straight line. You can put 3 cylinders per crankshaft pin. You can put a rotary, 360-degree, polyphase. You can have a V-block at whatever angle that you want. It's universal. This engine is closed loop. There is no emissions. Now I'm going to introduce to you the understanding of the applied application of this patent. This can be applied to a standard air compressor that we know of. It can be applied to an internal combustion engine that we know of, whether it be a 2-stroke, a 4-stroke, a Rankle, opposed, or oscillating cylinder piston, as in an air compressor refrigeration pump. In adsorption or absorption. Those cover all fluid dynamics, including the nominal displacement of hydraulics. All circuits. This is a circuit. This is a copyrighted circuit. The applied patent is to a standard air compressor, to a refrigeration unit, to a automobile, a submarine, an airplane, a spacecraft. So that's land, sea, and space. This solves all emission issues. There is no emission. The primary fuel is ocean water. The catalyst is in situ. The energy to produce this is proprietary. Now, let me introduce you the understanding of the advancement of all of those internal combustion style engines, hydraulics, refrigeration, with the co-designer of Arthur Devine. I'll introduce to you the Devine Allen nominal displacement absorption engine. This is an expansion cylinder. There will be no moving parts except for this. This is the piston. As the piston expands into a standing wave and contracts into a standing wave, the amplitude of the standing waves will increase the torque. This engine is a pressure engine. We can run at negative 30 inches of vacuum and make horsepower, or we can run positive pressure and make torque. Torque will exactly equal horsepower squared. So if I put in 6,000 psi, this will make 6,000 horsepower. squared, up and down, depending on load. It's torque that we're after to do the work. The horsepower will be trailing as amperage. As the piston rocks, you've got the expansion stroke, so that contraction from the spring tension recoil will help the bottom dead center pull the piston back. It'll, instead of pushing the rod back and having the other piston pull and stretch the rods, this will pull it back. Contrary to what happens in a normal internal combustion engine. This will be fixed. There'll be no wrist pin here. No wrist pin. Solid thing, connecting rod to the crankshaft. Like I said, you can have 3 pistons on 1 crank rotation. So that takes the that's a pretty awesome looking engine. Okay? That's a very awesome looking engine, in my opinion, if that were in a V. So you can do a polyphase in that. You can have 1 piston here and the other pistons here in that perfect polyphase angle. This engine has an efficiency rating to be determined. The fuel. The fuel is included as an application in this patent, but the formula to produce the fuel is proprietary. The fuel, however, is CO2. We're taking CO2 and making graphene O2. As the empathy changes from graphene to the ground state of carbon, there's your carbon fuel. So the fuel is this. G36-H18-O11-O72 C. As the power stroke comes up, makes its power, the fuel starts to cool at the empathy state. Once it compresses, the heat returns. The graphene fuel burns through a traditional spark. I get 20 degrees before top dead center. And 20 degrees after bottom dead center, or top dead center. And 20 degrees bottom dead center. before bottom dead center and 20 degrees after bottom dead center. Those are my spark curves. The catalyst proof that the catalyst is explosive has already been disclosed. On protonspintechnology.com and H hydrogen for power. However, as of this date, only the proof has been disclosed. No discussion, no math, no understanding, no applied patent, nothing. Just a proof of concept. No patent disclosure to date on the combustion of CO2 fuel and combusting CO2. So after the 44 minutes or 48 minutes, you've taken up the rest of the hour of this patent disclosure discussion. Thank you for your time. My name is David Allen Pukta, birth date 1970, February the 8th, 7:30 a.m. Hayward Kaiser Hospital, California. California driver's license number C64-92718. That's all you need to know. Thank you and have a good day.